Good afternoon. Welcome to our next Infogest webinar on food digestion. This is already our 14th webinar in our webinar series on food digestion in the run-up of our conference beginning of May, 3rd to 5th of May in Cork. My name is André Brodkorb. I'm based at the Teagasc Food Research Centre here in Moorepark in Ireland. So today we have yet another great speaker, Luca Marciani. And let me introduce you to the other panelists. That's first my colleague Daniela Freitas and Mackie from University of Leeds, and of course Luca Marciani. And we have Muireann Egan working in the background, organizing and managing the webinar. Over to you, Daniela.
Thank you, André. So I'm starting with a brief introduction to Luca Marciani. Luca studied physics at the University of Genoa in Italy. He then started working in the field of imaging and spectroscopy in Milan and London before joining the Sir Peter Mansfield Imaging Centre in Nottingham, where he was awarded his PhD in 2001. After this, he was awarded 2 personal fellowships to continue his work at the Nottingham Digestive Diseases Centre in the local School of Medicine, where he joined the faculty in 2010 and was recently awarded the chair in gastrointestinal imaging in 2020. His personal expertise is in imaging the human gastrointestinal tract using MRI. His research focuses on imaging gastrointestinal function in health and disease using MRI methods in combination with other physiological and behavioral techniques. Current interests include in-body imaging of foods, beverages, and formulations, intestinal fluid distribution, and the development of novel MRI tests for motility and transit with increasing focus in pediatrics. He has published 128 papers and 15 book chapters in this subject area.
Well, thank you so much for the kind introduction, Daniela. That's wonderful, and thank you to the organizers for having me. My experience with Infogest, excuse me, goes back to Wageningen. I think 2014. It was with the 3rd conference, and it's an absolute honor to be here with you today. I looked at some of the previous webinars. I looked at the names of the others I had to miss, and I'm going to catch up then on YouTube. And they are so famous. I get a bit of attacks of imposter syndrome being here today, so I'll try to keep up with their standard. I'll try to start sharing my slides and see if that works. So share. Does that work well?
Yeah, super.
Okay, let's see if I can get the little laser out. Okay, so my brief today was to talk about gastrointestinal tract physiology. GI stays for gastrointestinal here, not glycemic. It's always confusing. And food digestion, and using a vantage point, using an imaging device that can help you see things from a distance. And that was the idea of the title, having a crow's nest to look at physiology using an MRI lens. So that's my brief. And what I prepared for you today, apart from a little Wordle quiz on your right, so that I can keep you away from the inbox while I'm speaking, it's a brief introduction to our group and the rationale of what we do. I will give you a very brief introduction to MRI. I'm going to teach you everything you need to know in 3 slides. And then I'm going to go down into talking about the stomach, small bowel, and colon. I have deliberately tried to keep this more contemporary without going back to very old stuff. So I'm going to just give some panoramic examples of things that you can do in the synergy, the interface of these 3 sciences. And the juicy bit is at the end with the recent developments, and then I'm going to draw some conclusions. So MRI, most of you will know, is been invented in Nottingham. Here is Sir Peter Mansfield collecting his Nobel Prize for Physiology of Medicine. And many things in Nottingham are named after him, our beautiful imaging center here. But we also have other things. There's a tram that takes the students and the staff to the university named after him. And there is also a delicious British bitter beer named after him. So he's actually one of the famous people in our town. What many people don't quite know is that one of the first things that have been imaged using MRI is the gut, with the exception probably of a cross-section of a finger. And the application of dynamic imaging to study the insides of the body started actually with gut imaging. Since those old times, we're talking about 30 years ago, plus the group has developed. So that's a picture of our team. It's unfortunately a bit old because of COVID. We haven't actually met as a group in a pizza place for a while, so this needs updating. But if you count the heads at the moment associated with our group, there are 6 full academics, 3 of whom are medics, 8 research fellows, 3 are medics, 1 is allied health professions, and 11 PhD students, 6 of whom are allied health. I'm making a point about the allied health to say how we are interdisciplinary. We have a pharmacist, we have a dietitian, we have some radiographers, we have a nurse doing PhD in our area, not just the classic imaging people. So that's the group. And going back to the beginning of the story of the group, we made a conscious choice not to go and study cancer and polyps. So we launched ourselves into looking inside the gut, food and drinks, fluid devices, formulation, and especially motor function, motility, transit, transport, those kind of things. And along the diagram of the gut, there are a number of parameters that you can measure using MRI, from gastric volume, gastric emptying, layering. You can measure physicochemical properties with relaxometry. We can look at fluid volumes, transit, transport, and so on and so forth. So why is it interesting or important to do this? The rationale is that one usually gives an input to the system, food, very well characterized, food or beverage, and then goes off to measure something, blood values, blood sugar, hormones, satiety, food questionnaires, usually with a very well characterized intervention A versus B. And what we're trying to do with the imaging is to look inside the interface, the processes the input, to eventually try to link what's happening in the interface that generates the output. So that's the rationale, trying to say a bit more. It's not the answer to everything, of course. Trying to say a bit more about what the foods and drinks do in the body to generate the output. This is interesting to understand our endpoints, but it's also interesting, increasingly more interesting, to inform bench models. There are wonderful digestion static and dynamic models, and they are necessarily and beautifully simple in a way to be able to be used. But any additional information that comes from in vivo that can make it more in vivo relevant is very welcome. So this is where some of the parameters can go. And today also in the in silico modeling digestion, modeling absorption. So these are ways in which having in vivo parameters and measurements can help. And interestingly, if you substitute a basket of food with a bunch of drug capsules and tablets, the pharmaceutical industry has got exactly the same problem of trying to understand what happens to the tablets in the interface so that they can model drug absorption and dissolution. That's the backdrop of the rationale. And then we go about learning about MRI. The one thing I would like to take away from today is that MRI is a radio. It uses radio waves. So when we put a subject in an MRI, we basically put the subject in a big radio. If you think about piano keyboard, an electromagnetic spectrum piano keyboard, MRI is to the left, the deep notes, low frequency, long wavelength, very low energy. So it's safe to use. We scan children, we scan fetuses in the womb. This is opposite to the other end of the keyboard. So the high notes, high frequency, short wavelength, very high energy, where imaging becomes ionizing and damaging. So one of the beauties of MRI is that we can do it serially on multiple arms of studies and to children as well. How does it work? So the basic principle at the base of MRI is not different from gravity. If you put a sample of water in a magnetic field, you can transmit and receive radio frequency from it. That's just how it works. And is the chemistry experiment that the chemists, the NMR chemists, used to do since the 50s. So there's nothing strange there. The genius development was to understand that this, as I just told you, depends on the magnetic field. So if you change the magnetic field from left to right, you will put a special signature which makes this phenomenon different from left to right. And you change in a knowingly way from top to bottom and from front to back. And then you have superimposed a system to encode the space inside the body and being able to take images. So you then sample the signal and reconstruct with a simple mathematical formulation the image. I don't know if you can see me in camera, but the image, my nose gives it away. That there is a picture of me proving to you also that I do have a brain. Why is it taking over the world in radiology and in medicine? The reason is that an MRI picture like this one, where you have the head up here, this is the heart, this is the liver, and the feet of the person down here, is not a slice of the body like a slice of bread. It is a physico-chemical map of properties of those tissues, drinks and beverages and foods inside the body. And the reason it's a physico-chemical map is that what we use to transmit and receive radio frequency is actually water molecules there, hydrogen, proton. And these are quite small and very able to move around and sample the environment around them. So there is proton exchange, there is flow, diffusion, perfusion, spin exchange. They sense the micromolecules around, they exchange atoms and molecules. And this little reporter is able to give us information on all of these processes if we're able to tune our imaging to one or more of these processes. They happen with certain time constants, this mysterious T1 and T2, the one sees in the books. They are just the time constants with which these processes happen. That's MRI. Is a beautiful way of taking physicochemical maps of things in the body, including foods and beverages. So I move on to the various bits of the gut. The stomach, we start with the stomach, we ignore a little bit the mouth and the esophagus for now. The stomach is a reservoir, it's a big bag, and the first design is to accommodate food and drink when we eat. It's got motor function, so it's able to grind and mix food, so there's aspects of mechanical digestion, and it also secretes, so there is the beginning of chemical digestion, and is regulated by feedback. So the sensors lower down regulate the gastric emptiness, so the passage of food into the small bowel. Also has mechanoreceptors, so is able to feel the stretch and signal, for example, sensations of fullness. A very clever organ. And I'll give you here an example of how imaging of the stomach has developed. We have here the X-rays. Is not very useful for studying physiology of food digestion because you really need a lot of barium or bismuth, so salts that absorb the X-rays and gives you contrast. So apart from being damaging, it's actually quite unphysiological the way you would prepare the food. So that's not being used very much to image the things that we're interested in. Gamma scintigraphy in the middle is actually very, very clever technique. You need to put radiation in the food and then read the radiation from outside the body. The problem with this is that you don't get anything from the body, so there is this black picture. You need to put markers to actually realign the images from different experiments, from different timings. And you don't see what's happened to the rest of the food. For example, if you had liquid to the original radiation, you can't quite see how much it's got there, or the gas. So it is an imperfect way, although it's very sensitive to the things you label. An MRI as we were saying, is very, very clever in depicting not only the object of interest, which is the food and the beverages, the gases, but also the surrounding physiology. So that's the stomach. We were saying, let me see if I can start this one. Yeah, we can image serially. So one thing that we can do is to image at different time points, and the other thing that we can do is to image repetitive time points, so that we can create little movies of the stomach moving, and then use semi-automated or automated techniques like this one to measure the contractions and the speed and the velocity. So it's not just a static technique, it's a dynamic technique that we can image also motion. And I give you just some examples of recent bits of work that we've done to give you a flavor of the things that you can do. And I start with this one because it's got a diagram of a typical MRI day. So we get someone in, usually fasted, so that the bowel is in a nice empty state. Take some baseline measurements with MRI and with questionnaires, bloods, whatever you're taking on that experiment. Feed them, and then at interval, we pop them in and out of the magnet to repeat those things as long as digestion continues. So you need a little bit of planning, a little bit of understanding of how long it takes. This particular example, we were copying an old 1977 experiment by Professor Haber, where he wanted to study the effect of processing food on digestion. So we've taken the same meal, which was apples, and we've given them to people in chunks, so solid. We pureed with a professional cookie machine, or juiced in a proper food hole. So we had solid, pureed, or juiced apple, and they were all 600 ml, 178 kilocalories. Got a bunch of people, about 18, and then we ran the experiment, randomized, so that we avoid all the effects. This is the appearance of the apples in the stomach chewed. This is the appearance of the puree, spooned in, and the juice just drunk. Air doesn't give you an MRI signal, so it's black. So changing the physical appearance of the food, did it change gastric emptying? Yes, it did. That's the black curve for the whole apples, the curve for the puree, for the juice, as expected. And the feelings of satiety will go also in the same direction. So it's trying to put correlations between the physical properties of food, the physiology, and the behavioral scores. In a similar fashion, this was work done by one of our students with Unilever. There's an industrial part, it's all published. And we were looking at the effect of processing and stability. So we designed with the food manufacturer some clever emulsions, which were fine, so done with a microfluidizer, a bit of a painstaking adventure to make them, 0.4 micron or large, 6 micron. I think this is D32, but I would have to go back and look at it. And we give them to people as they were. So a coarse emulsion with liquid, and you would expect the droplets to float, so to come to the top of the stomach. We added just a little bit of leucospin gum to stabilize the coarse emulsion, so that the fat droplets would be distributed evenly and come out evenly with the empty. And then same thing done with the fine emulsion, but it was an order of magnitude smaller. Did the emulsions behave in the stomach as we thought? You can image them, and with MRI you can look also just at fat. You can kill the signal of water and look at fat. And this bright white wedge here in the stomach of this person is actually none than this one. So the coarse emulsion, which was meant to be unstable in the stomach, did float up, and you can expect it to go out last from the liquid if you stand up. And the other emulsions are reasonably homogeneous in signal. So we achieved this other condition. And did this change the physiological responses? Yes, it did. This is the fine emulsion, which you would expect with a much higher surface area to be much better digested and much more stimulating the hormonal responses. Empty slower, that's the middle effect, and then the coarse emulsion, which was unstable, emptied last. And this is reflected, for example, I don't show them here, but in the hormonal responses, CCK, and the pasta meal eater. So we give sometimes at the end of our experiment an objective pasta meal, so that on top of the behavioral score, you can actually measure physically how much people would eat. And the coarse emulsion that emptied faster and stimulated less the feedback responses. The people hungry, they ate more, and the other ones in a dose response way. So in a way, is designing different test interventions, checking that they're actually doing what they're supposed to do in vivo, and then measuring the responses to make sense of it. Much simpler. This was a study done on sports drinks, where the sports drink is meant for marathon people, marathon elite athletes, especially marathon athletes, have the problem that they need fluids and they need energy, but there is a threshold after which the gut, under stress, refuses to take too much fluid and too much carbohydrate, and then you get sick. And gelling the material in the stomach may help dampening down the symptomatic responses. The drink seems to work very well for the marathon athletes, but does it actually gel in the stomach? That was the question that we had. So the simplest thing to do is to design a not very big randomized controlled trial with only 8 people. And we produced a test drink as it is in the product, or the control just removing the gelling alginate and pectin, and run the study. And in this kind of MRI imaging, very bright is fluid, watery material, and darker is gel. So you can see in this case with the test drink, beautiful depiction of the gel that is actually, the drink is actually gelled, and then fluid have remained bordering and even with a wedge inside it. And if you image again, the gel was still there. So beautiful demonstration of mode of action of self-structuring gelling in the stomach. This is recent work done with Alan. We were wondering from all our images if we can actually measure the size of the food boluses. Boluses, boli, depends on your flavor. I call them boluses. I know Daniela calls them boli. Can we measure size of distribution? So we've taken retrospectively some of our MRI studies, and jointly with some help from our colleagues in Copenhagen, we've been measuring one by one all the little bits of food that we could see in the stomach after eating. So this is the first time point of imaging just after the volunteers had their meals. And the meals were very different. One was chicken and roasted vegetables on the left, bread and jam on the middle, and we will go back to that soon, and cheese and yogurt on the right. And we measured them all, and we looked at the differences in between the frequency distribution of particles. Depending on the meals, we change dramatically the size and the distribution. And then with some assumption, we measured, we calculated, assuming that every particle had the spherical, but they don't entirely, but assuming that they were spherical, we could infer on the surface area, which is what would be then available for digestion. And then we published this. It's a really nice study, first experience of doing this. It seems to work, and we plan hopefully to do a bit more of this. But that is again information that is precious for whoever wants to then model digestion in a static or dynamic system, because how big do you make the boluses, and then how many? That's more bread. I couldn't leave out Daniela's study on bread for 2 reasons. One is that it's a nice study, and the second one is that she's going to start forward from us. She looked at the boluses here, but then she looked across time, so changes of the appearance of food in the stomach. That's something that we haven't done yet with Alan. And she observed that the bread bits, very similar to the ones that we observed, little by little form larger agglomerates and increasingly lighter contrast, so they get hydrated. This is interesting because it's the mechanical and grinding action of the stomach, but is also showing how hydration takes time to happen from the stomach juices. So if you had a blob of bread with amylase inside, the amylase would keep working, although the blob of bread is ended up in a slightly acidic stomach. And the other thing I like of this study is that they've added some little frozen peas to the bread. And frozen peas happen to have a characteristic bright signal on a T1 weighted sequence like the ones on the side. This is something that colleagues from farmers in Greifswald in Germany do with the dried pineapple. You just hit the substance or a vegetable piece that has a characteristic signal. So they could follow the little piece because they're hard and see how they mix. And they fed the piece last from the bread and looked how well the stomach was actually mixing them and showing that the action is actually quite strong. But that is another way of looking at hydration, agglomeration of boluses, and also mixing action. I've got here a couple of pictures with some more curious accommodation. One is from carbonated drinks. This, although the paper doesn't quite show it, I think this is their more carbonated 3.2 volume soda drink. And these are axial slices, one after the other, so they're contiguous slices of the body, and black is gas. You can see how much gas 800 ml of carbonated drink would have generated, and how much stretch and accommodation the stomach had to provide. And I make the unthinkable on the right. I show you a CT image, computed tomography, because I just like it. It's not MRI. And you can tell it's a CT because the bones are really bright white. And this is someone who ended up in the literature as a case report because they've eaten 3.2 kilograms burger at a competitive speed eating event. And they ended up in hospital, not surprisingly, and they had to stay in hospital for 5 days before getting better. But the message from this picture is thinking about accommodation and imaging. Look how clever the stomach is able to accommodate this enormous mass of food. And yes, it took 5 days to empty it, but then it was fine and went home. So the stomach is genuinely remarkable. I passed down now, we're going to spend too much time. I passed down to the small bowel. Small bowel is longer. Again, very clever segmental mixing and propulsive motions. It secretes a lot of fluid. It absorbs a lot of fluid with nutrients. And it's all made by folds, villi, microvilli. So the surface area is huge for improved digestion. And it provides a lot of very good feedback mechanism is mechanical and chemical receptors. In reality, it's difficult to tell from the MRI images which bit of the bowel is which. You can follow a bit of the duodenum at the beginning until the ligament. You can follow backwards some of the ileum, terminal ileum from the colon where it attaches. But when you're in the wiggly bits, it's fairly difficult. Usually, this bit up here is judgment. It's very convoluted and it's fluid. It's not stuck inside the body, so it can change from day to day. So it's difficult, more difficult to image things in the duodenum. It moves and it's not fixed. I show you here a picture from Alex Manis, our colleague that works with a company that does automated image analysis software for the gut. To see the bowel this well, you need to inflate it, so it's full of oral contrast agent. But it's a nice way of showing how the bits of the bowel, the small bowel, that move, bits are quiescent, and if you watch it again, then this changes, and then it changes again. So it's working in different ways, in different places as it goes along digestion. But you can measure that. So we were, in this case, trying to look at what is the motility response of the small bowel to feeding. And very simply, we gave a tin of soup, 200 kilocal, to some healthy volunteers and just watched the bowel at intervals to see what he was doing. We took bloods, 2 questionnaires. And on the left here, you have a MRI image. We superimposed the motility map, the heat, where is red is motility. When there is nothing, there's nothing. And at baseline, there is a little bit of motility going on in the bowel, but not very much. As soon as you fed, you all get bright red hot. And this is motility happening. The interesting bit on the graph on the right, where there is some arbitrary unit of how much it moves, and then time. As a baseline, then we feed them, and then we measure. motility creeps up immediately, as soon as after feeding, to the top, and then decays slowly, and then there is a little rebound. So motility is maximal after a meal when you have just been fed. And this mirrors also the initial peaks of the peptides, CCKG, P1, PYY, they all peak early. And so this all interconnected and regulated mechanism. So this is what we were expecting to see, but we need to measure it to it. The motility responses, you can look, and we're interested also in diseases where the motility doesn't quite work as well. But the small bowel is particularly, and I'll show you in the next slide, an environment rich of fluid. So we were saying at the beginning that you can tune MRI to one process or the other one and look at some physical-chemical characteristic of the body. You can tune it to the anatomy, and here is a coronal picture. The head is here and the feet are down here of a person, and they have all the bits of the anatomy on show. If you just change one of the parameters on the scanner, you can kill completely the anatomy and look only at very mobile fluid water. This is something that the doctors do to look at the cholangiopancreatography scans, so the biliary tract and the gallbladder. But we use it to look at water in the bowel. So you can scan the anatomy and then turn on the water scanner. And it's interesting because if you let me step back a second to the overall physiology, there's quite a lot of fluid going around the bowel. You input about 2 liters a day. These are, of course, approximate numbers. You input quite a bit of saliva, and they all end up in the stomach. Gastric secretion, another couple of liters. Then you add bile, you add pancreas, and the small bowel itself secretes. And then there is absorption. The bowel absorbs between 7 and 8 liters per day, and the colon does very little secretion, a little bit, but it's mostly an absorptive organ, so he absorbs the rest, 1 or 2 per day. When you then look at the output out of the body from the rectum, it's actually very little, 150, 200, 250 ml per day. So most of the fluxes are input and then reabsorption. You can measure those. So a very, very good example of this is our 2014 experiment on FODMAPs, whereby carbohydrate sugars are either absorbed, malabsorbed, or poorly absorbed. And the hypothesis is that well-absorbed sugars, like glucose, would be absorbed very quickly, and so you wouldn't see very much water in the bowel. These are frontal pictures. The head is here, and the feet are here. That's the small bowel here. And you can see that there is not much white, so not much fluid inside after half a liter of water with 40 grams of glucose. You put some fructose. Fructose is malabsorbed by the small bowel. You would expect it to generate more fluid. And look at this. It's all lit up white bright with malabsorbed water in the small bowels. That demonstrates the malabsorption in one picture. What happens if you put them together? So not 20 and 20, but 40 and 40, so double up, but one is glucose and one is fructose inside the drink. Then you would expect that the body is kind of fooled into reabsorbing the fructose with the glucose. So you would expect the small bowel to hoover up all this fluid. And that is exactly what happens. The bowel has absorbed the fructose as well, instead of ending up in a situation like this. If you give fructan, that is not very much absorbed, not very much malabsorbed, you would expect it to go primarily towards the colon and do little effect in the small bowel, which is what you see. So this is really mode of response of the small bowel to just slightly different FODMAPs inside the diet. And I'll kind of on time, I will pass to the colon now. Colon is the last bit that we tackle today. Is a much wider and not as long organ. It's 1.5 meters more or less. He moves, so he's got again segmental mixing and propulsive contractions, a lot quieter and a lot more erratic than the small bowel. He secretes a little bit, but primarily absorbs and is a bioreactor where all our microbiota is living happily or unhappily, depending on the situation. When you do MRI on the colon, you can very easily measure volumes. This is a 3D reconstruction from one of our students. This is actually in a child. And then you can watch him moving. So we put a little bit of fluid in the colon so that it was much more visible. If you put your eyes here, slowly, 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 these are massively sped up. Can you see just a little bit of a mixing contraction there happening? And there's a bit of bouncing, which is respiration. The person is breathing, fortunately. And then no, it's happening. Then eventually, if I play it again, you see another, it places itself. The small bowel moving a lot quicker here. There is a segmental contraction here. Every now and then, if you put your eyes here to the bottom of this one, there is a massive propulsive contraction that moves material along. Watch it again. There it comes. So there are segmental and propulsive contraction. What's interesting to look in the colon? Well, a lot of things. One hot topic these days is the effect of fiber. And this is the study from Giles Major that was with us until recently. And looking at Ispagura. So it's an old effective treatment for constipation, fiber. And mode of action is thought to trap water, bringing more fluid, wet fibers, let me say this, to the colon, softening the stools and increasing colonic water content. But does he actually do it? So we did a small-sized randomized controlled trial, 9 healthy volunteers and 20 patients. We fed them psyllium for 6 days, and then we looked at the MRI in the morning of day 6. And this is a sagittal image of the colon. I'll pass it with my little laser pointer around so that you can recognize it. This is the ascending colon in the sagittal view. This image is quite chunky and it's bright. So you just learned before that bright in this kind of sequences is water. So we have increased the size of the colon and make it more watery compared to the control. They only had maltodextrin, and you see that it's smaller and it's darker. That shows you the mode of action of fiber into bringing water to the colon. We also took stools and measured the water in the stools from the other side, and there is a nice correlation for biological data. It's pretty good. And so some of the measurements that we make do correlate then with physical measurements of the stool. We've done the same with kiwi fruit. Kiwi fruit is rich in soluble and insoluble fiber. So we had, again, a bunch of volunteers, randomized controlled, and they consumed kiwi fruit for just 3 days. And in 3 days of eating kiwi fruit, their colonic volumes went up significantly by 17%. And in the time constant that relates to wateriness, which is T1, they all increased the wateriness of the colon. But one, that's one that did it significantly by nearly 30%. So you can look at, very simply with a few scans, at the effect of food material and mode of action of, we'll come back to them, kiwi fruit in a second. I nearly finished. We talked about gas. Gas is easy to image because it does no signal, so black is gas. And from the same study on the sugars that I have described to you before, we can look at fermentation of FODMAPs in the colon. So this is an image in the baseline. You see the colon is gray, and then we give them 40 grams of inulin and with a drink of water, and we image again at 4 hours, and this big black blob of gas has appeared from fermentation. The healthy volunteers would not quite feel it very much, but if you have a sensitive colon, more irritable bowel syndrome like, that is going to hurt. So is a way of looking at mode of action of FODMAPs in generating gas in the colon. You can actually quantify it. This is gas volume versus time, and that is the various curves. I'm about to conclude, but before concluding, I want to show you some recent developments, which I think are the juicy bit of the field. one of the developments is that there are many more people doing MRI in gastrointestinal tract for physiology and food. Alan is online. Daniela is online. She's moved to Cork, and I'm hoping she's taken the MRI skills with her, and we double up. Postmates in Utrecht and Wageningen is doing some beautiful work on milk and protein. Zurich has always been working in the field, and they wrote some seminal papers. There is more interest from the interface between medicine and food. So living in London, looking at FODMAPs again, Barcelona, looking at colon volumes, microbiota. And the other side of the world, there are 2 trials going on now in New Zealand, looking at kiwi fruit and milk using MRI. So it's nice to see that this is actually expanding and one would say booming. Other developments are the availability of upright scanners. This is the one that we bought thanks to one of the government grants that we demonstrating how you stand up. And when you take the MRI, if you look at the interface between gas and liquid, it's flat because the head is here and I'm standing up. There's fluid in the duodenum as well. The images are not as precise and crisp as the tunnel machines because it's the physics. But you can take now pretty decent upright coronal and axial images. There's so much to learn about this. Does it make a difference? Well, some crazy colleagues in Switzerland had one of these machines, and they put a subject upside down to look at digestion upside down. They just used water. And if you look at the graph that they published, it's actually not very different. It's not significantly different. It would make a difference if you had layers of nutrients, like the study I showed you with the fat. If the fat layered upside down, you would do the duodenum first. So there are things to learn here about upper digestion and also symptoms. But it's interesting that when you're upside down, if it's a clear fluid, actually digestion is not different. So it's not gravity; it is a pressure pump. The other thing which I did want to say towards the end is that these MRI data are getting noticed. Our kiwi fruit work, because we showed that the mode of action of kiwi fruit fiber is exactly the same of the ispagula. These data have entered a successful EFSA regulatory claim for the maintenance of normal bowel habits. This is work that we did with the producers of the kiwi fruit, and then they went with putting together other studies, of course, and then making the claim. But the MRI data were showing the mode of action, and they are now recognized as a regulatory grade, which is fantastic. So you can see a lot more of this happening to look at mode of action of health claims. And this one, I don't understand it entirely, so bear with me. I'll try to explain it to you as I understand it, is the relationship with microbiota. So we have a study now in cystic fibrosis, where we took a bunch of healthy volunteers and a bunch of patients with cystic fibrosis. And we studied gut function after a meal and took also microbiota. And the colleagues in Manchester did all the microbiota analysis. And they produced a paper which is in press now about the changes between cystic fibrosis patients and healthy volunteers. And also, what are the correlation with MRI parameters of gastrointestinal function? And the way I understand it is that the things you see on the graph are the species of the bacteria which are more different from controls to patients. And the green sticks indicate correlation with the metadata and the other parameters taken during the study. And the longer the stick, the stronger the correlation. And we can see here urocecal transit measured by MRI, colon fasting volumes measured by MRI, and small bowel water, like the water that I just showed you, measured with MRI. We did have something similar in a PLOS One paper from a couple of years prior, But these are the first demonstrations of relationship. Stop at that word. Relationship between our MRI endpoint of what food is doing with the physiology and the microbiota. So hopefully I'm on time. I hope I raised the task. We have talked about gastrointestinal physiology and food digestion using our vantage point of our medical imaging telescope. And I hope I showed you that the GI MRI not only is the answer to the little word here, but GI MRI is one of the answers to understand better what happens to the input, the food and beverages inside the interface, which is our body, and how that may link to the outcome endpoints. There is a huge research potential at the interface between the imaging, the physiology, gastroenterology, nutrition, dietetics, food digestion science, and we should actually dive in it because there's so much that we can do. I do note that there are an increasing number of groups working in the area, as I showed you. I heard that there is talk of ganging up together and work collaboratively in higher numbers, and I think that that's absolutely great. And there are exciting recent developments. I didn't have time to talk to you about pediatrics, for example. Pediatrics children are not small animals. They are actually a completely different beast, and there's so much we can do. And I'll stop there. And thank you for listening.
Thank you very much, Luca. That was a really great talk, and it has generated a number of questions. And as a member of the panel, perhaps I'm going to cheat by asking a question myself at the start. You kind of said there are some great developments kind of coming on board, and you mentioned pediatrics, but what about other parameters? I know that people have been interested in whether you can use MRI for measuring pH in the stomach.
There are a number of things in the pipeline. There are different ways of teasing these little reporters that are the water molecules going around the body. One is called magnetization transfer, so you measure how well they can exchange magnetization with things around them. One is CEST is called chemical exchange saturation transfer. There are ways of probing ability of exchange between things, and you can relate them, for example, potentially to pH using molecules that change the signal characteristics if they change the pH. There was on a different kind of physical principle time ago a paper looking at the pH in the stomach using an aluminum compound, changes the resonance frequency with pH, for example. But yes, there are all these things. Paul in Utrecht and Wageningen is looking at these kind of things for protein, for example, trying to link the signal to protein digestion with milk. And yeah, that is very clever stuff. And usually it needs some bench work, some calibration, some understanding on beakers and things of how the system works. When you find a strong enough correlation in a neat enough system, because probably a very complex mixed meal would be difficult to do, then yes, you can extract a lot of information. It's delicate. There are usually mechanisms where this thing that you're trying to measure causes a loss of signal. And there are billions of things in the body and in MRI that can go wrong and lose signal. So you need to be very careful that the loss of signal you're measuring is actually the one you want. But clever people can do it.
Yeah.
But yes, it's completely different. Think about instead of the little Muireann on the bench, they measure only T1 and T2, a spaceship. This is the leap.
Yeah, thank you. We've got, in fact, 3 questions from George Van Achen, and maybe I'll just pick a couple of them. So you showed data on the sugar-producing gas in the intestine. He says, how does a large volume of fructose retain for a long time in the small intestine feel?
That is a very good question. In most cases, not too bad, I would say. Not too bad. The small bowel is quite clever, and that kind of fluid we haven't quite seen spilling out on the colon. So the bottom end of the small bowel was able to regulate and eventually deal with it. And there are some unexplored, I think, aspects on bloating that could relate to gas in the bowel or fluid in the bowel, but I don't think it's been explored or understood entirely. In healthy volunteers, it's remarkable how much fluid you can have in the bowel, how much gas you can have in the colon, and they don't know they have it. The system is clever, but as soon as the pathway is hypersensitive or then yes, it signals symptoms.
Yeah, okay. And another question he has is it true that volume or bulk in the small and large intestine drive the distal transport?
The distal transport. I'm not sure I got the right answer. Larger objects, like the camera pills, they travel faster than smaller objects, like the little radiopaque markers. So size does make a difference in the small bowel. The system is very clever. So if it's not dysregulated, then it would cope with volumes and move them accordingly, and segment them, and try to cope with those. But if you have a large input, is a pipe, eventually you need to push things down the line, otherwise it wouldn't work. So I would say it's a complex relationship. I'm not sure if I answered George entirely, but that's more or less.
Okay, I'll let Daniela lead with a couple of questions.
Thank you, Luca. That was an excellent presentation. So we have a few more questions here. So one of the questions is it possible to get an accurate measurement of opening and closing diameter of the pylorus and amplitude of the stomach waves, especially in terminal antral contractions?
So there's a paper from Zurich that went to measure the pyloric opening, and I know about it because it goes beyond the old classic idea that it needs to be a millimeter particle, otherwise it doesn't come out. It can be bigger. And in terms of amplitude of contraction, that's easy these days. That's easy with the semi-automated measurements. You need to understand that dimensions is not pressure. So if you squeeze the stomach and keep squeezing, the manometry measurement will go up to the roof. But if you close the stomach and keep squeezing, the MRI will still say 0. So they are physical dimensions, different units.
Okay, thank you.
I have a quick question because we have to finish soon. I have to have show a couple of slides at the very end, including some tourist information on Ireland. But Luca, compliments. I envy your big instruments that you have, and you create, great images. And in my experience, when you, present food research or food digestion, you can show, graphs and all this. But if you show a good image, it tells a good story. And some of the images that you produced with Alan was the basis of, a PhD thesis of Annabelle Mollet-Cabero, who is in the audience right here. So I have one quick question. Actually, one was preempted by you, because when I saw you sitting in NMR, my first question was, did any curious scientists, go upside down? And obviously there are a lot of curious scientists. I would be one of them. What happens? But if you go into space, is there any information on that? Complete.
It's a very question. I don't know. It is a pressure pump. The idea that the contractions push things down in its gravity is wrong. The pylorus closes, and the contraction, then there is a jet of flow backwards, and then a pump opens up and relates it. If you look lower down the bowel, sometimes you see flow events where the walls are not moving, so the pump is somewhere else. I would imagine that the pressure pump would work in the absence of gravity quite well, providing your esophageal sphincter that doesn't fail, because otherwise you choke. I would think it could digest quite nicely. They do, don't they? So,
just one last and very short time resolution. So time resolution, we have seen a couple of images. What is the challenge there? What can you do in time resolution?
It's such a good question. What I usually get from the pharmacist is how low can you go? MRI lives in the millimetric world, so the 100 micron stir layer on the bowel. No, it's a millimetric world, and at this time we can scan those movies for the full motion with sub-second resolution, second, just below a second, which for the physiological process is plenty much. We've actually scanned a lot less faster than we could, because there's no point in taking images which you sample with the frequency that you need. For motion is fine. For resolution, you can infer from microscopic events some signal changes macroscopically. So you can infer some, but we live in a millimetric world and second, sub-second.
Very good. So thank you very much, Luca, and thanks to the panelists as well, Daniela and Alan. I just have a couple of slides just for your information. We're about 70 live attendance, so between Zoom and the YouTube live, and usually we get a couple of hits, a couple of hundred hits on YouTube then afterwards, so it's good enough attendance. But we are looking forward to the real event, meeting, person to person. I think I can't wait, Okay, thanks again, Luca. I just have a couple of slides. My internet connection is a little bit slow today, so if I'm breaking up, just tell me, Muireann, and you might show the slide, show my slides. Okay, here we go. Can you see my slides? Can you see my slides?
Not yet.
Not yet. So I am.
There we go. No, you're okay.
Yeah. Okay. So I just want to have a couple of slides on the Infogest. So the chair is Didier Dupont and vice chair is Alan Mackie, and we have 6 working groups. And these 6 working groups will meet after the conference in Cork. So on the Thursday afternoon, I will show the time plan later on. Thursday afternoon, the working groups will meet. So please have a look out for the emails that are coming from Didier Dupont on the action, on the registration for the different working groups. You can also follow news on the LinkedIn Infogest group. If you are not a member yet, please send an email to Nathalie Lamar or Didier Dupont, and you can be a member of the Infogest. It's wide open, really. We also have a YouTube channel. We have a YouTube channel. All the webinars are on the channel, and this, including this one. So at the moment, this is live, so uncut, and I will crop the beginning and the end afterwards. So the Food Digestion Conference is approaching fast, 3rd to 5th of May. Please don't miss the early bird registration. That's 17th of March. You can see here there's a QR code for their website, and on the top right is a QR code for the LinkedIn event. So we post news there. I just want to have some tourist information. So the airport in Cork is open, but there are not very many flights because of the slow start after COVID-19. So the most likely arrival airport will be Dublin Airport. So you can book a coach, a bus, an air coach, aircoach.ie, and that's a direct, very cheap bus, actually, 3.5 hours from Cork Airport to Cork City. You have to book it in advance, mind you. Accommodation We got a few questions on accommodation. Of course, you can stay in the venue or very close to the venue. However, they are a bit on the pricey side. That's again, after COVID-19, all the prices in the hotels went up just because the hospitality sector was really battered. You can also look, on booking.com or on Airbnb closer to the venue, and that's in Douglas. So the venue is right here, that's Cork City. Douglas is walking distance, or in Cork City. And I just before I joined, I just put that in, Cork City to the Maryborough Hotel. There are buses, very regular buses. It takes about 15, 20 minutes. So you can stay. There's plenty of accommodation in Cork City. So this is the program. Tuesday afternoon at 2 o'clock we will start. Tuesday, 3rd of May. We have a nice reception in a lovely venue in the hotel on the Tuesday evening. Long day on Wednesday. I think we will start at 8:30, not 9, but 8:30. And we have a cool gala dinner in a barn just outside Cork. It's about 45 minutes on by coach. So we will go directly from the long conference. Yeah, I think you have half an hour, 3/4 of an hour. And then we go by coach to the gala dinner, food and drink and a bit of crack, a bit of fun, and back into Cork City. Thursday morning, we have the conference again, the short break, lunch break, and then Thursday afternoon are the working group meetings. So please, if you're interested in the action of Infogest, that's really the place to go in the afternoon. And we'll be split into 3 groups. First, I can't remember which group was first, and then after an hour and a half, we swap over. There are 5 themes. We have about 150 submissions, and if I remember right, it was just over 100 submissions for oral presentations for 24 talks. So it's pretty competitive, and all of them are good. I just have one slide here on the tourist information because we got a few requests, where to go. The obvious point of information is Fáilte Ireland. It's one of our sponsors as well. There's another one, Discover Ireland, the Wild Atlantic Wave, which is a roadway all along the coast of Ireland. It's a spectacular route. If you want to stay a day longer in Cork, at Kinsale. So this is Cork City here. Here we go. Kinsale is right down here. It's about 30 minutes on the bus. Or if you go over here to Killarney, it's about an hour and a half. It's a touristy town, but touristy in Ireland is still pretty tame. If you have a car, I would recommend to stay in the south here. This is West Cork. Down here again, a spectacular Ring of Kerry and Dingle. Mind you, slow driving, small roads. It all takes some time. If you have any more questions, send us an email. Okay, so our next webinar is on the 6th of April, and we're very happy to have Paul Mahan from the Massey University talking. Please note, because of time difference, it will be 8 o'clock Dublin, so 9 o'clock continental time. And he has a very interesting topic of food digestion and sustainability. What is the link? And he has some very intriguing data to show. I also show another workshop. That's actually next day, Thursday of 7th of April. It hasn't been finalized yet, but please go onto the LinkedIn Infogest site. You'll probably see an update soon. So it will be a workshop, 1 o'clock to 5 o'clock Dublin time. So this is European time, this Dublin time, on dynamic in vitro digestion models. And it's a joint workshop between UNGAP as a cost action and Infogest. And here you see different speakers presenting different dynamic models. So that is tentative, so it's likely to change. Okay, so that was my last slide. Thanks again for attending, and thank you for the panelists and Luca, of course. Goodbye.